Hello and welcome. In this video, we're going to be talking about solving nonlinear systems. So solving a system where we don't have two lines, as we've looked at in the past, but where we have a line and a quadratic, or two quadratics, or a circle and a line. So we're going to be really looking at how do we identify those solutions if we're given a graph, and how do we find those solutions if we're given the two equations. So let's go ahead and jump right in. So in previous classes, we've talked about nonlinear systems a little bit in Algebra 1, and we focused on the idea of a quadratic and a line, which we're going to revisit that idea today. But it's possible that if we have a quadratic and a line, that they don't ever cross. That would mean there's no solution. That they cross once, that would mean there's one solution. Or that they cross twice, that would mean there's two solutions. Similarly, if we had two quadratics, they could never cross once, or cross exactly twice. So the idea of comparing two functions, one of whom is not aligned, that's what a nonlinear system of equations is. And since we've talked about systems before, we can apply the same strategies when we are solving them. So let's start by looking at graphs. So the solutions to a linear or nonlinear system are the points where our two functions are crossing, the points that exist in both functions. That's what makes them solutions. So if we're given a graph, all we have to do is identify the coordinates where they are crossing, and then we can state what our solutions are. Notationally, we're going to write our solutions as the ordered pairs in set notation. So this ordered pair here, x is -1 and y is 3. And this ordered pair here, x is +1 and y is 3. We're going to write the point on the left first and then the point on the right. So in number 2, our solution is here at this coordinate, which is 0, -1. And there's only one coordinate, but one of the reasons we like to use this set notation is because it distinguishes that this is a solution set as opposed to an interval representing something else. What you'll notice in example 3 is that these two quadratic functions, they aren't ever going to cross. One of them is going up forever, one of them is going down forever, and there are no intersection points. So we would say that there's no real solution, or we could draw our set notation with nothing inside, the empty set, because there are no solutions. So if we're given a graph and we're just being asked what are the solutions to this non-linear system of equations, all we have to do is identify where they intersect. But what happens if we don't have graphs? This leads us back to some previous ideas that we have learned in other classes about solving using substitution or elimination. So let's go ahead and look at some examples where we can solve using substitution. So substitution is the method that we have used previously where we solve for one variable and plug that variable into the other equation so that we have one equation with one variable. This works great when it's easy to isolate one particular variable. Most of the time when we're talking about quadratics and or circles in a system with lines, we're going to isolate y. So the very first thing we're going to do is we're going to solve one equation for a variable, usually y. We're going to plug that into the other equation and solve for the remaining variable, usually x. And then once we find x, we can work backwards to find our other variable, y, and still write our answers as ordered pairs, just as we did on the examples where we identified from a graph. So if I look at number 4 here, the first thing that I notice is this second equation. Well, first thing I notice actually is that what I'm talking about is a quadratic and a line. And we've talked about those can cross twice, they can never cross, or they can cross once. So what I'm going to do is I'm going to take the linear equation, the one that doesn't have an x squared, and I'm going to subtract x on both sides so that I have isolated y, which is what step 1 was asking us to do here. Now I'm going to take that equation and I'm going to plug it into my original or my other equation, the one I haven't used yet, everywhere that I see a y. So that equation says -1 equals x squared plus x minus, and then I'm going to replace y with -x plus 4. Now I'm going to distribute -1 equals x squared plus x minus 4 if I distribute that negative sign. And I'm going to get everything on the same side and combine like terms. So x squared plus 2x, if I add 1 on both sides, that's going to give me -3. And now I have a quadratic. And if I'm solving this quadratic, I can use factoring if it factors, the square root method, the quadratic formula, complete the square. Any of those methods are going to work here. That's why we spent the first half of this chapter learning them. This appears to factor. X squared is x times x. If I want it to multiply to be -3, I can use -3 and 1. And this is going to give me the two solutions, -3 and +1, if I use the zero product property. So don't box your answer here, though. Our goal was not to find just x, but to find the coordinates where they cross. So once I find x, now I need to find y. If x equals -3, I know that y equals, I'm going to write this up here, -x plus 4. So the opposite of -3 plus 4, that's going to give me 3 plus 4, so 7. So when x is -3, y is 7. When x is 1, y equals the opposite of 1 plus 4. -1 plus 4 is going to give me 3. So when x is 1, y is 7. So there we have our two solutions that we can write in set notation. So I'm going to encourage you to pause the video and try and work through number 5 on your own, starting with taking that linear equation, the second one, and solving for y. Then unpause the video and see how you did. All right, hopefully you had time to work through this. This is going to be y equals -2x plus 7, and I can plug that in for this y here. So 5 equals x squared plus 2x minus the quantity -2x plus 7. So if I distribute that negative sign, and then subtract 5 on both sides and combine like terms, I end up with this quadratic here. This quadratic also factors. 12 is going to be 6 times 2, so x plus 6, x minus 2. That's going to give me two solutions, x equals +2 and -6, and then I'm going to plug those back in to find y. If x equals, I'm going to start with -6, then y equals -2 times -6 plus 7, or 12 plus 7, which is 19. So -6, +19 is our first solution. If x is -2, y equals -2 times 2, or -4 plus 7, which is going to be 3. So our second solution is the point 2, 3. So for both of these problems, we had a quadratic and a line, and they happen to intersect 2 times. This was solving using substitution, which is a method that will work when you can easily isolate a variable. Let's talk about another way to solve, which we have done in the past, and that's elimination. Now, we have used elimination a lot this year when we have been solving 3x3 systems. So hopefully this is a quick refresher at a much easier level where we just have two equations and two variables. So some key things. Most of the time you're going to be eliminating y because you're going to have x squared and x. If we're talking about a quadratic, it's going to be easiest to eliminate y. So make sure that you line up your variables so you're not accidentally combining 2x squared with 2x because those aren't like terms. So first thing, make sure that you are eliminating y, but while you're doing that, you're lining up your variables. You may have to multiply by something. You may just be able to add your two equations together. Once you've eliminated y, you're going to have one equation that just has x, so you're going to solve that equation for x, and just like on the previous examples, you're going to work backwards and plug those values in to find the y values of your ordered pairs and write your final answer using set notation. So let's go ahead and look at number 6 here. The very first thing I'm going to do is I'm going to just rewrite this so that my variables are lined up. So I'm not changing anything here. But the way this is set up, my x's and my y's and my constants are not lined up. So I'm going to actually just take this second equation and I'm going to rewrite it. 0 equals x squared plus 2x plus y. Oh, that's so much easier to look at. And now I don't actually need to multiply anything anywhere to eliminate a variable. I have negative y in my first equation and positive y in my second equation. So if I simply just add these together right now, my y's are going to add to be 0. If I add -2 plus 0, I get -2. 2x squared plus x squared is 3x squared. -5x plus 2x is -3x. And I can go ahead and move everything to the same side. So now I have a quadratic. It doesn't look like this is easily going to factor. I'm not seeing right away how it's going to. This looks like a complicated complete the square problem, so I'm going to go ahead and just jump into the quadratic formula. So x equals the opposite of b is positive 3 plus or minus the square root of 3 squared minus 4 times 3 times 2 all over 2 times a. I'm going to go ahead and simplify this, 3 plus or minus. If I simplify inside this radical, this is going to give me 9 minus 24. That's going to be negative 15. Now, we have spent some time talking about imaginary numbers, but when we're talking about where two different functions cross, we are not going to include imaginary solutions here. So since I have 3 plus or minus the square root of negative 15 all over 6, that's going to mean that there's no real solution, and for systems, it's acceptable for us to say these two functions, they just don't ever cross. There's no real solution. So I know that's a little different than what we've been doing earlier, where we've just been talking about one quadratic, but the answer here is that these two functions never cross. So I'm going to encourage you to rewrite number 7, line everything up, or maybe just straighten it out a little bit, and then eliminate y and see if you can work through this problem on your own, and then unpause the video and see how you did. All right, so I'm going to start by just rewriting the two functions. They're mostly lined up here, but I'm going to line them up a little bit better. X squared plus y equals 2. And again, I notice right away, I don't have to multiply by anything to eliminate my variables. My y's are already going to eliminate. And if they weren't, it's likely I would just have to multiply one of my equations by a negative sign so that my y's would eliminate. So if I combine like terms here, 2x squared plus x squared is 3x squared plus 4x is going to equal 0. Negative 2 plus 2 is 0. Now, something I notice here, this has a greatest common factor. Yes, you could use the quadratic formula. Completing the square would be pretty complicated. You can't solve using square roots, but I notice that these two things have an x with both of them, so I can factor that greatest common factor out, and then I can set each factor equal to 0 using the zero product property. So this is actually solving by factoring. This is going to give me my two x values, which are 0 and negative 4/3. And now I'm going to go back and I'm going to find y, and I'm going to use the second equation, x squared plus y equals 2, and I'm going to go ahead and solve for y. Y equals negative x squared plus 2. So if x is 0, y is going to equal 0 plus 2, which is just 2. So if x is 0, y is 2. If x is negative 4/3, y is going to equal the opposite of negative 4/3 squared plus 2. Now remember that negative sign comes into play afterwards, the one that's in front. So this is negative 16 over 9 plus, I'm going to convert 2 to be 18 over 9. So this is going to give me positive 2 over 9. So when x is negative 4/3, y is 2 over 9. So number 6 was an example of two quadratics, and they actually never crossed. Number 7 was an example of two quadratics, and they crossed twice. So they had two different solutions. The last thing we're going to do is we're going to incorporate one more function. We've been spending a lot of time talking about quadratics and lines. What we're going to do in our last couple examples is we're actually going to bring back the idea of a circle, just briefly review that, and see how that comes into play when we're looking at nonlinear systems. All right, a little quick review from geometry. A function of the form x squared plus y squared equals r squared is the equation of a circle. So you'll notice both x is being squared and both y is being squared, and that's equal to the radius squared. And this is the standard form of a circle that's centered at 0, 0. If our circle is centered somewhere else, just like with quadratics, we'll see another number in here. So this would be the equation of a circle that is centered at the point 2, negative 4, and that has a radius of 4. So just kind of getting that idea, a little refresher in here. We don't need to remember all of the basics with a circle in order to understand how to solve the system, which is what we're going to focus on in this video. So if we have a circle and a line, they could never cross. They could cross once at a tangent point here, or they could cross twice, creating a secant line here, a line that crosses a circle exactly twice. How that geometry sort of comes into play with what we're doing is really not any different. You can still use substitution or elimination. Most of the time you're going to need to use substitution, because what you're going to need to do is plug something into this y so that we can square it and then simplify. So typically substitution is going to be the easiest way to go when you have a circle as one of your two functions. You're still going to solve for x, then plug that back in to find y, and then write your answer as ordered pairs. So let's go ahead and look at number 8. Number 8 already has y isolated, so y is equal to this, and we're going to plug that into y in our first equation. So I can say that 10 is equal to x squared plus the thing I'm going to plug in for y squared, so negative 3x plus 10. Just as a reminder, negative 3x plus 10 squared means that we're multiplying negative 3x plus 10 by negative 3x plus 10. So you can use the distributive method twice, you can use the box method. However you're going to go about doing it, you need to make sure that you're multiplying it correctly. So let's go ahead and multiply that out. That's going to get us here. Then let's combine like terms and move that black 10 from the left over to the right-hand side. And now I have a quadratic that I need to solve. The first thing that I notice is that all these numbers are divisible by 10, and since I'm solving, I can just divide them all by 10 to give myself some significantly smaller numbers, and then that looks like it's going to factor x minus 3 squared, or x minus 3 times x minus 3, which means we're going to have one solution, and that solution is going to occur when x is equal to 3. Now I just need to plug that back in to find y, which we know y equals negative 3x plus 10. So if x is 3, y is going to equal negative 9 plus 10, which is 1. So this line crosses this circle, or touches this circle exactly once, and that's at the point 3, 1. I'm going to encourage you to pause the video and work through example 9 on your own, and then unpause the video and see how you did. Remember to take your time with that multiplication. If you need to draw the box method or the area model to multiply out, go for it. If you need to show more steps, that's totally acceptable. So I started by substituting in x plus 2 for y, then I expanded. Now I'm going to move everything to the right-hand side. And then again, I noticed that everything here is even, so I'm going to go ahead and simplify that by dividing everything by 2. And then this looks like it's going to factor x plus 4, x minus 2. So I'm going to get x equals negative 4 and positive 2. And then I'm going to go ahead and find y. If x equals negative 4, y equals negative 4 plus 2, or negative 2. If x equals 2, y equals 2 plus 2, or 4. So my solutions are going to be the points negative 4, negative 2, and positive 2, positive 4. So hopefully working through all those examples is really giving you an idea of how to approach these system problems, and now you can practice it and really build that skill set. So key ideas in this section: the solution to a nonlinear system is any coordinate where our two functions cross. We can solve those by using substitution or elimination. We can identify the intersections from a graph, and that's going to help us find those solutions. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.